everyone, Teacher Chris here, and today we will talk about Haworth Projection Formula and the steps on how to do it. So without further ado, let's get started. Okay class, so today we will talk about Haworth Projection Formula. But before we go to the step-by-step process on how to do the Haworth Projection Formula, I will give you some insights and trivia on where did the Haworth projection formula came from. It was actually developed by British chemist Walter Norman Haworth, and in honor to the developer, it is named after the inventor or the developer. Okay? So Haworth projection formula is a two-dimensional structural rotation that specifies the three-dimensional structure of a cyclic form of a monosaccharide. Because in nature, the pentoses and hexoses uh, are abundant, we know it, but the open chain structure that we know in Fischer projection in our other videos, the pentoses and hexoses are more abundant in a cyclic form. In order to explain the cyclic form, Mr. Haworth make a formula for these types. Okay, so let's go now on the step-by-step process on how to develop or how to make this formula. So the first step, we have actually a Fischer projection, or we call this one as an open chain projection or open chain type of structure of our D-galactose. Now, what is the first step for Haworth projection? The first step is let's lay down or make it into a horizontal position. So, how to determine or how to make the laying down of this compound? Let's just focus first on the head, or we call the CHO group or the aldehyde group. Okay? If it's on the top or it's the head, it will be on the right position. Then we have the tail or the CH2OH. It will be on the left position when we lay down the molecule. So if it's top, it goes to the right. When it's at the bottom part, it will be on the left side of the molecule. Now, the right parts or the right arms will be, or right arms or the right molecules that are attached will be at the bottom part or the bottom area. Then the right or the left part will be at the top part of the compound. Okay. Now, after laying it down, we will move it into a bend position, or para lang siyang natutulog na tao na naka-bend position, in which the, let me get this one first, in which the CHO now, I just used the stick formula on it, will be in this position. Then the CH2OH will be at the other side. Okay. Now, what's the essence of this one is that this C double bond O here, there will be something that will happen to it later on. Okay? That's why I made it into a stick model. Now, the next step we have here is that there will be a twisting of the three substituents in our carbon 5. So, as we look at the carbon 5, let's first number it. The CHO will carry, or the C in the CHO will carry the first carbon, second carbon, the third carbon, the fourth carbon, and the fifth carbon. Now, the sixth carbon will twist and move its position to the upper part in which we can find the hydrogen. Okay? Then the hydrogen will twist or move to the lower part or at the bottom part in which we can find the OH group. After that, the OH will also move to the position where we can find the CH2OH. There will be a twisting and exchanging of positions These are important and vital in order to form the cyclic ring. Okay, now I use the stick model on the OH because in this part, together with the aldehyde group, will have a specific reaction between them. So let's go now to that step. So here, in this part, let's look at the oxygen. Okay, in the oxygen part, it actually has two lone pairs on it in its valence electron configuration. This oxygen carries actually a partially negative charge because of its electronegative ability or electronegativity. Now, our carbon here will be attacked by this oxygen because the carbon here also having a partial positive charge on it. This causes now the attraction between the partially negative oxygen to the partially positive carbon. This will form a bond. Okay? As you can see on the next picture here, it forms a bond. Now, this is an unstable bond because the carbon, as you can see, it has already the four electrons that are shared towards the attaching atoms and molecules on it. Now, what will happen? There will be a breakage of bonding. Try to look at the double bond here between the oxygen and the carbon. It breaks up. One of its bond in the double bond will break, causing now the oxygen to have a negatively charged, and it stabilizes our carbon because it only now has four bonding electrons that are shared towards its attaching molecules. Now, the oxygen here becomes a positively charged because it is still unstable. What will happen is it will break its bond between the hydrogen that is attached to it. It will break, causing it to have an electron that is bonded, and it becomes stable. And the hydrogen will now be free, having a positive charge kasi it will have one electron on its valence electron. Now, this positively charged hydrogen will be attracted or bonded now to the negatively charged oxygen at the bottom part. This forms now a specific bond or formation in which we can form a cyclic monosaccharide or a cyclic D-galactose. This cyclic positioning or the cyclic structure is what you call pyranose. Okay. What does pyranose mean? It is derived from the word pyran. Pyran is a specific compound in which the oxygen is bonded to the 5 carbons, okay, forming a cyclic or heterocyclic ring. And it has double bond, okay, and that is a pyran. Okay, that's why it was derived from that word, causing it to be called as pyranose. Now, this carbon here will also have a specific name. It is called the anomeric carbon. When we say anomeric carbon, it means that it is the hemiacetal carbon present in a cyclic monosaccharide structure. It is the carbon atom that is bonded to an OH group and to the oxygen atom in the heterocyclic ring. In layman's term, it is the carbon in a heterocyclic ring in which this one that was bonded by an OH or what you call the alcohol group. And while it is bonded to the alcohol group, it is also bonded to the oxygen in a heterocyclic ring. Okay, so that will be the name of that carbon. Let's go to the next one. Now, in this formation, according to studies, the cyclic type or cyclic D-galactose will have two forms. Okay. The first one, we have the alpha D-galactose. It was called alpha D-galactose because of the presence of our CH2OH and OH. Now, the question is how to name an alpha. So it will be alpha if the OH and the CH2OH are on the opposite side. Okay, let's clear that one. When OH is at the bottom, in which in opposite side on the CH2OH which is at the top, this causes now the naming of alpha on the D-galactose. So it is called now an alpha D-galactose. What about if it's on the same side or both of these indicators or attaching compounds are on the same side? This will be called the beta-D-galactose. Okay? Para madaling maintindihan, look at the symbol beta on the word both. Okay? If both of them or both of these two compounds are at the same side, automatic you will name it into beta or it's on the beta position. That's the difference. Okay. Now, this is for a D-galactose or in the D isomer. What if it is an L isomer or an L-galactose? In an L-galactose, titingnan natin or we will look at the arrangement of the substituents or the attaching compounds kung saan sila makikita. When we say D-galactose, the position of your CH2OH, ito yung first indicator, the D-galactose will always have the CH2OH at the top part of the cyclic ring, while the CH2OH on the L-galactose will always be at the bottom part. That is the first indicator. The next indicator to know is by looking the OH and the CH2OH. Okay. But don't look on the first carbon. Saan nga yung si first carbon? Ito yon. Oh, sorry for that one. That is one. This is yung first carbon natin. Now, let's only look at the second, the third, the fourth, and the fifth carbon. Yun lang yung titingnan natin. Because those are having the OH that are attached kung saan makikita, ma-determine natin, nag-invert ba siya. When we say invert, when we look at the D-galactose, when the OH on the second carbon is at the bottom, automatic with an L-galactose, the OH is at the top. When we look at the third carbon, the OH is at the top. When it's an L, it will always be at the bottom. Same as in the carbon 4, in which the L-galactose is or can be found under or at the bottom. Then, when we look at the D-galactose, it always be at the top. Tapos, yung CH2OH natin will always be at the top. And yung CH2OH natin sa L-galactose will always be at the bottom. Yun yung rule. Okay? Don't interchange it. If you can see the positioning in that position, automatic masasabi mo na D or it's an L. Now, how do we designate the word or the symbol alpha and beta on this position? In this case, both the CH2OH are at the same side. Katulad silang nasa bottom. Therefore, this is in beta position. That's why we call it the beta L-galactose. Yun lang yun. Huwag nyo nang guluhin yung isip nyo. When both of them are in the same side, automatic that is an beta L-galactose. Okay? Now, what about the next one? Paano naman si alpha? Si alpha will always be on the opposites. Kung makita nyo dito, the CH2OH will always be at the bottom kasi L yan. Then, let's look at the OH on the first carbon. It is at the top. Automatic, opposite side sila. This causes the formation of an alpha L-galactose. Yun lang yung indicator or way para madali natin silang maname and we can designate the correct the correct symbol and notation on the compound. Okay? So next, we have, what about, di ba, ano yun, D-galactose? It means it's an aldose. What about if it is a hexose that is a ketose? For example, I have here a fructose. And by the way, the pentose that are ketoses or pentoketoses will not have a Haworth projection. Why? It is different from the it's different from the aldoses that the pentoses and the hexoses will always have a cyclic form in nature. But in the ketose or ketoses, the most common found in nature are only, and in the cyclic ring are the hexoketoses only. They are only the ones that can be found in nature that are in cyclic form. Yun lang yung kaibahan ni ketose at ni aldose. So, how do we form a D-fructose? This is a hexoketose. Heto yun. Iba yung formation na nabubuo. In this part, the ketose will always have a C double bond O group sa second carbon niya. Okay? Not like the aldose that we need to go to the first carbon because the first carbon in the aldoses will always have the C double bond OH. While in ketose, it's the second carbon that has a C double bond O. So, ibig sabihin, di natin gagalawin si first carbon. Only the second carbon. And as you can see, we only have 1, 2, 3. We only have 3 chiral carbons also. Not like the aldose. So, the formation is, si C5 or si carbon 5 will be having the OH. Okay? The OH here will have to break. The O here that can be found is actually from your carbon 5. Anong itsura nun? Ganito. Si C, may bond niya na OH, same as what we have in aldose. So, you have fifth carbon, fourth carbon, third carbon, second carbon. Okay. This one here, the second carbon carries the double bond O and the CH2OH. This one, the oxygen, same rule. It is a very electronegative element or atom. It has 2 lone pairs. This will undergo or having a partially negative charge, and the carbon here will also have a partial positive charge. They will be the ones that will bond, and the H or the hydrogen attached to the bonded oxygen will break, and this causing to have a positively charged hydrogen. And also the double bond O here, the double bond on between your carbon and your oxygen, one of its bond will break, causing the carbon to be stable and oxygen will be stable. The oxygen that is bonded first to the carbon will have a negatively charged. This will attract or will bond to the free charged hydrogen or positively charged hydrogen to be bonded together. This form this OH. Ito siya. Then, we have now the formation of, you call this one as furanose. It is from the word furan. The furan is different from pyran because as you can see, it is a heterocyclic ring that only having 4 carbons and 1 oxygen bonded to form a ring. Same as a furan. Furan is only having 4 carbon atoms and 1 oxygen in a heterocyclic ring. Ganyan yung itsura niya. Tapos may double bond yan na dito. Yan. Okay. So that is your furan. Or that is the one that derives the name furanose formation or structure. Now, how to name this one? We need to look at the fifth carbon and the second carbon. Okay? Don't mind the first carbon. Okay? Kahit CH2OH yan, don't mind it. The only thing you need to focus is the OH that is attached to the second carbon and the CH2OH or the sixth carbon that was attached to the fifth carbon. If they are opposite, when the OH is at the bottom and the CH2OH is at the top, automatic that is an alpha D fructose. Kung baliktad, yung OH naman yung nasa taas, automatic it will be called as beta D fructose. Kung baliktad naman lahat, automatic that is a L isomer or L fructose. Same lang yung naming or the way we name the cyclic form on the ketoses will always be the same on the naming of our aldoses. Okay? And hope you understand the lesson that I gave you. That's it. That is sorry, nabulol. That is all, folks, for today. Hope you enjoy our lesson and hope you learned something from it. Again, this is Teacher Chris and see you on our next lesson. Bye-bye.